All right, let's jump right in. We all kind of think we've got solar panels figured out, right? More sun hits the panel, you get more power. Simple. But what if I told you that sometimes making a solar panel cooler can actually make it produce less power? I know, it sounds completely backward, but it's a real head-scratcher that engineers are dealing with as we speak.
Yeah, you see, for all their amazing tech, solar panels have this hidden flaw, a secret weakness, and it's tied directly to the very thing that's supposed to power them, the sun itself.
And this number right here, this is the whole problem in a nutshell. For every single degree Celsius that a solar panel heats up, it loses about 0.5% of its efficiency. Now that might not sound like a huge deal, but on a scorching hot day, trust me, that adds up really, really fast.
So this brings us to what we could call solar power's hot problem. It's this fundamental paradox that actually puts a cap on how much juice we can squeeze from the sun.
I mean, just think about that for a second. The very sunlight that's supposed to be making all that electricity is also basically baking the panel. And that heat makes the panel worse at its job. It's this constant tug of war, between grabbing the good energy and getting rid of the bad heat. So what do? How do you even begin to solve a problem like that?
Well, some researchers came up with an unbelievably clever solution, a solar panel that literally cools itself. And you want to know the best part? It doesn't use a single watt of extra electricity to do it.
It's called a natural convection cooling loop, or NCCL for short. The whole thing is passive, which is just a fancy way of saying it runs all by itself. No pumps, no power, nothing. It just harnesses the simple laws of physics to get the job done.
Okay, so how does it work? It's actually genius in its simplicity. Kind of like a lava lamp, really. So first, sunlight heats up both the panel and the fluid sitting in this little channel on top. As that fluid gets hot, it gets less dense, lighter, and it starts to rise. That pushes the cooler, heavier fluid down into a heat sink to cool off. And then that newly chilled fluid gets sent right back to the panel to grab more heat, starting the whole cycle over again. It just goes all day long, for free.
But, this brilliant idea created a new puzzle. What's the absolute best liquid to put in this thing? And to figure that out, the researchers set up a little competition, a coolant showdown.
So, in one corner, you've got your tried-and-true classic, plain old water. It's everywhere, it's cheap, it's see-through. And in the other corner, the high-tech challenger, an ag water nanofluid. Now this stuff is water that's been beefed up with microscopic silver particles. It was literally designed to be amazing at sucking heat out of things.
Now you look at these two, and it seems like a no-brainer, doesn't it? The nanofluid is the superior coolant. It's engineered for this exact job. So it should keep the panel colder, which should mean more power. I mean, that's just common sense, right?
Well, you can probably guess where this is going. The results were not what anyone was expecting. This is where the story gets really, really interesting.
So first up, let's talk temperature. And just like they thought, the fancy nanofluid won. You can see it on the chart. The panel cooled with the nanofluid was definitely running at a lower temperature than the one with just water. Okay, so far so good. Check.
But here is where things get really weird. They went and measured the actual electrical output. So the panel with no cooling, it was chugging along at just under 15% efficiency. The fancy nanofluid panel, the colder one, edged it out a tiny bit, 15.08%. But get this, the plain old water-cooled panel, remember the one that was running hotter, it just completely smoked them both, coming in at 15.45%.
And that brings us right to the heart of the mystery. How in the world did the warmer panel end up making more electricity? It feels like it breaks the one rule we thought we knew about heat and solar panels.
The answer, as it turns out, is that temperature is only one part of the equation. There was another massive factor in play here, one that everybody was missing.
To really get it, you've got to look at this graph. Think of a solar cell as a really picky eater. It can't just use any old sunlight that hits it. Nope. It can only eat light from a very specific slice of the rainbow, this useful blue area here, to actually make electricity.
So what about all the rest of the sunlight? All that other energy outside of the blue zone? It's completely useless for making power. All it does is get absorbed and turn into the exact thing we're trying so hard to get rid of, waste heat.
And that was the nanofluid's fatal flaw. It was an amazing coolant, sure, but it wasn't perfectly clear. Those little silver particles were actually absorbing some of the sunlight before it ever reached the solar cell.
And the worst part? It was absorbing light right between 340 and 510 nanometers, smack dab in the middle of the cell's favorite meal. The coolant was literally stealing the panel's food. This table just lays it all out, plain and simple. The nanofluid? Amazing at cooling, but terrible at letting the right kind of light through. And the pure water? Yeah, its cooling was just good, not great, but its light transmission was excellent. It let all the good stuff, all that useful energy, get straight to the solar cell.
And this, right here, is the big lesson from this whole thing. And it's not just about solar panels, not by a long shot. This is about, well, everything.
I mean, the researchers themselves said it best. Just making something colder by itself doesn't guarantee you're going to make it better. You have to look at what you're giving up to get that lower temperature.
And that's the real takeaway here. The best solution is almost never the one that's perfect at just one thing. True breakthroughs, true innovation, that happens when you understand all the complicated trade-offs and find that perfect sweet spot, that balance between everything. In this case, a little extra heat was a price well worth paying to get a whole lot more useful light.
It makes you wonder, doesn't it? Where else in our lives, or in technology, are we so hyper-focused on perfecting just one thing that we're actually making the whole system worse? It's a pretty powerful thought. Sometimes the simple, balanced solution is the best one of all.